We're really happy to welcome Pablo Iglesias to give us the last of our three plenary presentations. And Pablo has been a very important contributor to the field of computational cell biology for many years, with a real focus on cell migration and more specifically, how cells decide to move in specific directions, so directional cell migration. And he developed this model, which is very famous and which has given people a way to think about this, called LEGI. So it's always important to have a cute acronym, right, Pablo? So LEGI is, I think it's local excitation, global inhibition, that can help explain how cells detect small gradients, external gradients, and can amplify those gradients internally to move in a specific direction. So that's something that he actually did implement in virtual cell about 10 or 15 years ago, and led to some very important papers. And lately, he's been interested in some of the molecular mechanical features of cell migration. And I think his group has even used SpringSaLaD more recently, and I guess maybe he'll say something about that in his talk. So Pablo Iglesias from Johns Hopkins, thank you very much for agreeing to speak with us.
Thanks, Les. Let me see if that works. Okay, great. I think you can see my slides. So I gave Les, when he asked me to give this talk, a very short title, but I've expanded it just to highlight the fact that the work that I'm going to describe today would not have been possible without SpringSaLaD. And so I'm going to go through, in I guess, a fair amount of detail, the models that we did. Before I do that, I just want to introduce three people who were collaborators with this. The person there on the left is Alma Plaza Rodriguez. She's a graduate student in the program of molecular biophysics here at Hopkins. And the way this all started was actually 3 years ago. She was signed up to attend this conference. Now, if you're familiar, 3 years ago was not a good time to sign up for a conference. She was the first virtual, I guess she had virtual attendee at these conferences. But she learned how to use SpringSaLaD then, and so everything that I show you in terms of result, well, almost everything, is due to her. The woman in the middle is the little part that doesn't belong to Alma. This is Lee Nguyen, and she is an experimental biologist. We made some predictions with SpringSaLaD, our simulations, and she actually went and confirmed them. And the partner in crime here on the right is Doug Robinson. He's a cell biologist in the School of Medicine. We've been working together for a little over 20 years. And in fact, what I'm going to show you there is really work that we've been, our first published paper was in this work is 2006. So the title of the talk, and I should say that this has been published. It was published, I believe, in December in Biophysical Journal, and Alma will be at the Biophysical Society meeting next week. So if you're there and you care to get more details, please stop by and say hi to her and ask her questions. I should say that this is her talk, that all the mistakes are definitely mine. So just to give you a sense for what it is that we're looking at, Doug, there's a program in arts and biology and life sciences at Hopkins. So occasionally we get these master's students who do absolutely beautiful work. And this was a depiction of what the cortex looks like. You see several molecules there, or several filaments. You have actin, myosin bipolar thick filaments. There's a few cross-linkers like cortexin, filament, and alpha-actinin. But basically, what usually is thought of as something as a mesh work is really just a composite of many molecules. And so we wanted to capture that in models. Now, the specifics of what we're trying to understand is mechanosensation. And this was work that our first collaborative work with Doug. I had a student who had background in electrical engineering and biochemistry and wanted to combine the two. So she built an apparatus to aspirate cells, and she was looking at cells during cell division. And what she found is that when she aspirated a cell that was about to divide, myosin actually left the cleavage furrow and went to the site of aspiration. And what you can see that it's sort of the arrow in 169, that as it's been aspirated, all this myosin accumulates at the site of aspiration. Now, in these dividing cells, what would happen is that the myosin would actually pull out of the pipette, and then the cell would go happily and divide like it was going to. Now, we found several molecules that do this, and the other sort of real crucial molecule is cortexlin. And I should have pointed out that this is a dictyostelium cells, but we've seen this sort of accumulation in a lot of mammalian cells. Now, we have generated a model, continuum model that describes this. And what we found in one of these works, Loew, who's a postdoc with Doug, is that we get different types of accumulation. So what I'm showing you here in the top is myosin, sort of like what you've just seen. And we created a continuum model that could explain how like force-induced changes in binding rates of myosin monomers could actually lead to accumulation. And our models are by no means perfect, but actually captured a lot of that accumulation. We had several cross-linkers that showed similar behavior. And again, that we could capture that. That movie's not showing, but it's all, oh, there it goes. And then, interesting enough, there were several other molecules, including filamin, which doesn't accumulate at the tip of the micropipette, but actually more at the neck. And we conjectured and sort of argued that the difference here is the sort of change in the cortex. So a dilation could be measured in some ways, where shear could be measured in different or by different biosensors, and that actually would lead to different accumulations. Sorry. And again, we could do these continuum models that could explain this process. Now, now I have to tell you the IQ gaps. Now, dictyostelium has IQ gaps, like mammalians, cells do, but they're a little bit different. They actually, even though they're called IQ gaps, they actually don't have a lot of gap activity. Now, the interesting thing is that there's two of them, and they both, IQ gap 1 mechanosenses. But if you delete IQ gap 1, the process, this mechanosensitive process is still active. If you delete IQ gap 2, then suddenly you lose mechanosensation. You can aspirate and neither cortexlin nor myosin go to the pipette tip. But if you delete both of them, you gain back this mechanosensation. So the conjecture was that somehow these are doing some sort of competitive binding on the mechanosensitivity or on the molecules that achieve this mechanosensitivity. The other thing that we did, so this was the conjecture. So IQ gap 2 inhibits mechanosensation. IQ gap 1 does that. IQ gap 2 inhibits this inhibition. Okay, and so that's how you can actually get mechanosensitivity. Now, further studies showed or led us to this following notion of a contractility kit. What we discovered experimentally, I should say, Doug discovered experimentally, is that these molecules or macromolecular entities actually form likely in the cytosol before there's any force accumulation, and that this is sort of poises the cell in order to, in the presence of a stress, actually to move towards the cortex and enable this accumulation. So that's our working hypothesis. So we have this pre-assembly in the cytoplasm, and that this enables the cell to respond quickly to mechanical stimulus. So where I came into in this process is that we wanted to see whether this was actually going to happen. And so we wanted to do some sort of simulations that would actually recreate the building of these contractility kits, as we call them, where they assemble, how they assemble, and the different roles of the IQ gaps in doing that. I mentioned mediate mechanosensitivity. We haven't really done any mechanical force on these models, but I'll talk maybe a little bit about that at the end. So, no, I should also say that we have a ton of data in terms of binding affinities of the different elements of these mechanosensors, of cortexin, myosin, the IQ gaps, and a lot of other cross-linkers. Now, this is way too complicated. What I heard from the last talk, I completely agree. You know, when you go build a model, build it simply first. So that was what we aimed to do. Now, SpringSaLaD was perfect for us and for many reasons. One of them is, even though I'm a computer engineer, I don't really like to develop software for such. I'm trying to answer more a biological question. And so I'm very happy to use good software elsewhere. And I had a lot of experience with virtual cells. So, you know, the presence of SpringSaLaD was a welcome addition. We could enter the PDB files sort of to give the structure, looking at different domains and so on. As you're probably aware, but you know, the fusion is done through Langevin dynamics, binding, etc. is done through this modified Urban-Chapman stochastic simulation algorithm. There's different types of reactions use a Gillespie-like algorithm. Now, one thing that I told you had a lot of data, but most of the data is given in terms of interaction of molecules. If you measure a diffusion coefficient for a molecule, it's the whole molecule. It's not the specific domains like you model in SpringSaLaD. So there was a lot of, even though we had all this data, how to turn it into a SpringSaLaD model was something that Alma was struggling with. So what she first did was just look at things like diffusion. And so she looked at single molecules diffusing in the environment and basically measure the mean square displacement of these molecules and build up a polymer like that. So she did size 1 on the left, which is just a single domain. Then you have these polymers she went anywhere from size 1 to size 20, measure this mean square displacement, and then compare it to different models. So this is what the data looks like for polymers of different size, from the single monomer all the way up to size 20. And what you see is that on average, you get pretty much a straight line as a function of time, which is what the theory predicts. And we fit that to this model of what the diffusion should be. And from that, we obtain diffusion coefficients for the polymers. Now, we did this for a lot of data. What you're seeing here is different diffusion coefficients measured. And then what we did was fit the mean to this. And what you can see in sort of the dotted black line is that the diffusion coefficient for the coil or the polymer is roughly 1/n of the diffusion coefficient for the bead. Okay? And this is a well-studied model. This is sort of the Rouse model of diffusion. But we could use that, since what we have is diffusion coefficients for whole molecules, we could use that to look at the diffusion coefficients of the different domains. We did something similar with binding. So in this model, which I don't have a movie, but basically we just took two different types of molecules, A and B, that would form a complex C. We specified a binding KD, and then you compared what we were getting in SpringSaLaD to the theoretical basis for this. And what we found was that, sure enough, it fits very well. So we get a p-value of 0.999. So that that sort of gave us a sense for the accuracy of these models to recreate what we did experimentally. Now, let me tell you a little bit about the models, the specific models of the contractility kit elements. So we're going to include 5 different elements. I think it's 5. Cortexin occurs naturally as a dimer, but the way we defined it in SpringSaLaD is that you have these 4 domains, and they're at the two ends of this long spring-like connection. There are two domains which allow you to bind IQ gaps, either IQ gap 1 or IQ gap 2. But because of stoichiometry, we know that IQ gap 1 can bind twice to a cortexelin, but IQ gap 2 can only, twice, and IQ gap 2 can only bind once. So the way that we did this is that one of the domains, which I'll call QA for just identification, can bind both IQ gaps. QB can only bind IQ gap 1. But we implemented an allosteric reaction such that if if QA bound to IQ gap 1, then QB could only gap, I said that's bad, but basically to enforce that stoichiometric condition. The other two domains are one to bind a lipid, which would be essentially the membrane, and the other one to bind myosin 2. Okay. The two IQ gaps look like this. There's a cortexelin binding domain, and so I wrote IQ gap there. I meant myosin. Okay, so both of those can bind either to cortexelin or myosin. And then on the membrane, we have these lipids, which are meant to represent PIP2 because we know cortexelin binds to PIP2. And they have two domains, a membrane anchor and a head domain, which binds to cortexelin. Now, the more complicated molecule is myosin. Myosin exists as a functional monomer, which is actually a dimer. It has these two head domains, which are your H. Then along the neck, it has both essential and regulatory light chains. Within that neck region, we included 3 binding domains. 2 of them are to IQ gaps, that's QA and QB, and a third one to a cortexelin. And we did the same sort of allosteric model that we did for cortexelin for myosin binding the IQ gaps. Along this tail region, we included 5 dimerization domains. These are the D1 to D5, and 5 tetramerization domains, T1 through T5. Now, the way these work are as follows. So myosin, these functional monomers will form dimers. And the way that has, and these dimers are sort of parallel. So you'll get two of these myosin functional monomers come together, and they do that by binding the Ds, but in matching parallel. So D1 of one to D1 of the other, etc. Okay. Once that happens, what we have is that binding transition causes an allosteric transition that enables the T domains, the tetramerization domains, to bind. When they do that, they actually bind through anti-parallel. Okay, so in this case, T1 goes to T5, etc. Okay, and you can get higher order myosins, but it's through this tetramerization domain. Okay, so this tetramer at the bottom could bind a dimer above in anti-parallel format. Okay, and that's how you can build thick filaments. Okay, so these are, those are cartoons. This is what actually looks like in SpringSaLaD. And I'm just going to show you one simulation of the contractility kits building. Okay, and my apologies, it's probably a little choppy, but you can see individual cortexelins. Those are sort of the cyan-colored barbell-looking molecules. You can see, excuse me, much bigger assemblies, both on the membrane, because they're bound through the cortexelin, through the lipid, or off the membrane. Okay. And in fact, let me just show you sort of snapshots from that simulation, or a different simulation, showing in the bottom 3 here, you see 3 large macromolecular ensembles. 2 of them are off the membrane. This third one on the right is attached to the membrane. Okay. So these are the sort of simulations that we did, and obviously changed different parameters to get some insight into the process. So the first thing we wanted to do, since we've gone through these assumptions, we just wanted to make sure that the experiments, are a realistic simulation of what's happening in real cells. So a lot of the data that was obtained for those KDs is based on fluorescence correlation spectroscopy. And the idea there is that you measure fluorescence in a very small volume of a cell. And by looking at cross-correlation or autocorrelation, you can get diffusion coefficients or binding coefficients. Okay? You do this by looking at molecules that are tagged with different colors. So we basically did the same thing, but with our simulations. And so this is just an example of looking. So the idea is that we had this modeling environment. We'd look at a small sample and look at how different, I call this fluorescent fluctuations. Nothing fluorescent about it, but just the presence of cortexlan in this smaller volume and how that fluctuates over time and also concentrations. Now you can plot the cross correlation between these two different molecules, IQ-GAP1 and IQ-GAP2, for example, tied to cortexlan, and look at how that varies as a function of time. And from this data, you can then recreate, or you can obtain KDs. Okay, and so this is what the KDs that we got for different simulations, and by and large, they were very close to what had been measured experimentally. Okay, and so what that suggests is that these, the simulation was actually fairly accurate. Now you see a large spread, and that's because it's a very small volume, and so that you're going to get a natural fluctuation. I don't have the experimental data here, but our variance is small compared to what you measure experimentally. So there is a lot of, here on the right, I write experiments. I did not have a sort of a confidence interval, but the confidence interval is actually much wider than it is in the experiments. So, but by and large, our simulations captured that fairly well. You can do the same thing with a single molecule to get diffusion coefficients. And again, what we got was very similar to what we had measured experimentally. So again, the simulations which use these approximations because forced by the domains can recreate the binding and diffusion of the whole molecules. Now we wanted to ask about what sort of contractility kits we measure. And the idea is as follows. So here you have sort of a cartoon of the four molecules. You have IQ-GAP, you have cortexlan, you have myosin. And so we know experimentally that you have, if you get rid of IQ-GAP2, you have a mechanoresponsive contractility kit. If you get rid of the IQ-GAP1, it becomes mechanosensitive. But we did not know, or in fact, there was no experiments on the basis of what happens actually if you have both of these two. And what we found experimentally is that, in fact, about 50% of the identified contractility kits are what we called ambiguous. These are functions, or these are two plots. On the left, you see sort of the contractility changes over time, both the size and the number. And within that number, we found on the right-hand side, and the gray tells you that roughly half of them are ambiguous. And by ambiguous, we mean they contain both IQ-GAP1 and IQ-GAP2. And they can do this in different ratios. So this is more or less a snapshot of the ratios that we would see. They could be as simple as 1-to-1 or 2-to-1, etc. And remember, these things can build quite large. So that's how you could get a case where you have 10 copies of one IQ-GAP1 and only one IQ-GAP2, for example. Lee, as I mentioned earlier, she was an experimental biologist, and she went and actually then did measurements of these molecules. So what she did is she tagged one IQ-GAP with green fluorescent, the other one with a red, looked at what happens when you have just the fluorescent molecules on the right, when you have a dimer of the fluorescent molecules, but not attached to IQ-GAP1 and 2, or on the left, IQ-GAP1 and IQ-GAP2 tagged to different molecules. And using the same procedure of the fluorescence correlation spectroscopy, she could actually find that there is a statistical significant difference in that there is binding of these two molecules. Okay, and so that sort of showed that the at least one prediction of the model was actually borne out experimentally. The other thing that we were curious, I mean, we had done this in the environment that we used was originally just a cube, 200 nanometers on each side, and this is what happens in terms of the contractility kits, where they're formed and where they stay. And by and large, what we found is that most of the contractility kits were attached to the membrane. Now, we varied the dimensions of this of the environment to just look at different situations. So keeping the volume constant so that we don't have to worry about changes in terms of number of molecules and so on. What we would find is that as we increase the z direction, so in this case we quadruple the z direction, sort of, and therefore lower the surface to volume ratio, the formation of the contractility kits is primarily on the cytoplasm. Okay, and though those contractility kits do tend to move towards the membrane. When we increase that even more, so in this case, it's 20 times the z direction or z dimension as the previous simulations, that's really pronounced. Now, we think that this is a lot more realistic in terms of what the surface to area volume you would get from a cell. So this sort of confirms what we had thought, that these kits build or are assembled in the cytoplasm, but they can easily move towards the membrane, or in our case, really would be the cortex, where they can actually bring together, mediate mechanosensitivity. Okay. The other experiment that we did, we looked at what happens when you eliminate one of the IQ gaps or the other IQ gap, and sure enough, what we found is that when you eliminate one IQ gap, the binding of the other IQ gap increases greatly, and that's both to cortexin or to myosin. Okay, and that's not hugely surprising, because we're in the sense that we're thinking of this as competitive inhibition, but the model certainly fit into that. We also looked at the effect of the IQ gaps on binding, and what we found is that in the presence of both IQ gaps, you get smaller or smaller KDs for the binding of a cortexin and myosin. So the IQ gaps are helping get cortexin and myosin together, and we know that it is the union of cortexin and myosin that allows the cell to sense these mechanical stresses. So in conclusion, just what we found, well, as I mentioned, we found that the polymers in SpringSaLaD follow a Rouse-like polymer diffusion relationship, which I think is very useful for anyone else who's going to do a model like this. We developed this coarse-grained molecular model describing CK self-assembly. We found that the diffusion coefficients varied, but they were, we were able to recreate experimentally measured values. We had at least one prediction, which is that the existence of these ambiguous kits, and in fact, they are the most common ones that we saw. Roughly 50% of them are in of what we saw experimentally, and that was confirmed. And then we had this notion that it's heavily dependent, or the location is very dependent on surface to area volume, and that in fact, in the more realistic ranges of the surface area to volume, those kits are forming in the cytoplasm. And I think the argument for why that happens is that it's so much easier for molecules to diffuse and meet each other in the cytoplasm than it would be in the constrained environment near the membrane. And then finally, comparing the normal mutant distributions shows that the IQ gaps function to maximize a contractility kit size and enable cortexin and myosin to meet more easily. So that's what I wanted to say. I didn't put a sort of future work, but one of the things that we would like to do is, well, we want to take this knowledge that we've gained from looking at this molecular level view of contractility formation, but actually maybe then incorporate that into our continuum models. Okay, what difference? None of those continuum models simulations that I showed you included any IQ gaps or this notion of contractility kit. So if we can use that to go back to those models, see what difference that may make. We would also, ideally, we'd love to be able to look at some force dependency, which could be done by, we don't really incorporate force directly, but if that can change some of the kinetic coefficients between molecules, depending on whether force is being applied or not, would be very useful. So anyway, thank you for your attention. And as I mentioned, these are different students students and postdocs over the years that have worked on this, with the two in red of the ones directly affecting this paper. And I want to thank Les for developing SpringSaLaD, because as I said at the beginning, we would not have been able to do this work had SpringSaLaD not been available to us.